Hi everyone, welcome back to Physics 11. So some of you asked me about going over question 11 from Conservation and Energy worksheet. So question 11, we have a pendulum that is 1.2 meters long. If the pendulum is pulled until it makes 25-degree angle to the vertical, what is the speed of the pendulum bob when it passes through its equilibrium position? So the equilibrium position is basically when it makes 90 degrees to the top mounting surface, so maybe the ceiling. And the hint says determine the vertical drop of the pendulum bob first. So whenever you have a pendulum, you're going to have to find the difference in heights. Now, one thing to keep in mind with pendulums is that the length of the string, or it could be like a shaft or whatever solid piece that connects the pendulum to the fulcrum point, is the same length. So it's always going to be 1.2 meters, no matter what position it's in. So for example, if I draw my pendulum here, this is 1.2 meters, right? And this is 1.2 meters. So this is still the same length. So this does not change. So what are you trying to find here? Well, what you're trying to find is the change in height. So you're looking for your delta H. So you're looking for this change right here. So this is your delta H. So then in order to find this, we need to know what this length is. So let's call this length X. And now, as you can see, we end up with the right angle triangle here. And we also know that the angle is going to be 25 degrees. 25 degrees here. So because you know the hypotenuse, okay, and you're looking for the adjacent side, your X value, not the 1.2 is this whole thing here. So again, 1.2 goes from the top to the bottom of the bob here. But you need to know the X value. You have to use some trick here. So hypotenuse and adjacent is going to be cosine. Once you know your X value, then you can find your delta H, right? Which is going to be the vertical drop that the hint is telling us to find. So let's do that. Let's find our value for X. So in this case, again, I'm going to write cosine theta equal to the adjacent over the hypotenuse, which in this case is going to be our X and 1.2. So I'm going to replace my values with theta with 25, and adjacent is going to be replaced with with X. That's the unknown, and hypotenuse is 1.2 meters. So X in this case is going to equal to 1.2 times cosine of 25 degrees. Again, make sure your calculator is in degrees so you won't get the wrong answer. So 1.2 times cos 25 is 1.08756 and so on. So this is in meters. Now what I suggest you do whenever you actually use this value in your calculations later on when you're actually looking for the speed is you use the exact value, which in this case, this thing is your exact value. So instead of using some approximation, use the exact value in your calculation. So anyway, it's about 1 meter or so. So we know it's going to be, the delta H is going to be about 0.2 because this is 1.2. But let's see how we can find that speed that it's asking us for. Now in this case, we're looking at change in potential energy to change in kinetic. So we're looking at the equation that states that change, let's say if you have positive change in potential energy, so delta E potential is going to equal to negative change in kinetic energy. So remember, if you have potential energy as it transforms, you have to lose potential energy to gain kinetic energy, or if you have kinetic energy that's transformed into potential, basically one of them has to be negative, which means that you're losing that and it's transformed into the other form. So let's take this equation and expand it. Well, delta, remember, delta means change, which means final minus initial. So I can expand this and say, well, instead of delta, I can write it's going to be the final potential energy minus the initial potential energy. Okay, now this is our initial point, right? Because we're looking at speed here. What is our V final at this point? So this is initial point, this is our final point as it goes through the equilibrium point. So on the kinetic side, we're going to have a negative, so don't forget the negative. Make sure you put this in parentheses, otherwise you'll get not necessarily the wrong answer, but you might end up with a negative there, so be careful with that. So negative goes in front. We have E EKF minus EKI. And as far as notation goes, I normally use the 0 or the naught to show the initial, but with energies, because there's enough letters and sometimes it gets confusing, so I use interchangeably. For some reason, I always use I whenever I deal with energy, but normally I use the naught for everything else. So anyway, let's expand this further. So let's look at our diagram here and think what's going on. So at the initial point, we have no kinetic energy. So the bob is not moving. So that means that initial kinetic energy is going to be 0. So this term we can reduce right away. Okay, so no initial kinetic energy. And then at the bottom here, it's going to be the lowest point, which means no potential energy. So we can get rid of this guy. So all we're left with is just the two terms. We're left with just the final potential energy. Sorry, should be initial here. So again, we are left with just the final potential energy and final, hold on. I reduced the wrong one because this should be the one that goes away. Okay, so the final goes away, the initial stays, so we have only potential energy at the beginning, only kinetic energy at the end. So as you can see, we have this EPI equal to, in this case, this terms went away, so we left with negative EKF. So because we have negatives on both sides, actually, they become positive. So you can multiply both sides by -1. Now let's write this out a little further. And we know potential energy is mgh, so we're going to write mg times h initial equal to kinetic energy, which is mvf squared over 2. And we're looking for the velocity. So that's the goal here, to find the speed through the equilibrium point, so vf. So notice that the mass is not even given in the problem. Why? Because it cancels out. Because we have mass in both terms and it's the same, so it will go away. So now we're left with just the g times height and then vf squared over 2 on the right side. So all we have to do is now solve this for the velocity, and that's all we gotta do here. So multiply both sides by 2, you get 2ghi equal to vf squared, right? So the next step is then let's take this and solve it for our velocity, which is going to be the square root of all this, 2ghi. Okay. Next, we're going to plug in our value for our hi. We know that, again, our hi is going to be our delta H that I labeled here. So I guess I could have really relabeled this as my hi here instead of delta H. Or rather, this is fine. This is delta H. This would be my hi, right? This at this point. So this is my hi, and this would be my H final here at the bottom. The difference is delta H. So anyway, I still need to plug that in here. So I know that the X value is 1.2 times cos of 25, and hi is going to be the difference between 1.2 minus this. So when I plug this into here, like I said, instead of rounding, just keep the exact value. So we have 2 times 9.8. The hi is going to be 1.2 minus, let's see, we have 1.2 cos 25. That's what we need to plug in. So that's going to be our hi value here. So we're going to plug in 1.2 minus 1.2 cos of 25. So when you do your calculation, you're going to do this all in one go here on the calculator so you don't end up with rounding mistakes. So 1.2, and I'm going to do this in reverse. I'm going to do the brackets first, of course, BEDMAS. So 1.2 minus the 1.2 times cos of 25, that's going to be 0.11 times 9.8 times 2, that's 2.2. So just to show the intermediate steps, this is what I'm getting so far, and I'll just use the square root button next just to get the final answer, just so you can double check your middle steps. So something like this keeps going here. and then take the square root of this, and we get VF equal to 1.48 meters per second. So that's our final speed here. So the answer provided in the answer key is 1.49, and that could be just because of the proper number of sig figs when you round. So because we have a difference here, this would be 1 decimal place, and all of this you would have to round to 2 sig figs, which means that here you would have to round to 1.1. So if you have 1.1, that's 1 decimal also, which means this should be 2 sig figs in the bracket here as the final answer. So the answer should only have actually 2 sig figs. So the answer key is not even right. So it should be 1.5 overall. So the answer should have 2 sig figs. But anyway, those would be the steps. So sig figs is put aside. These are the proper steps for solving pendulum problems. So you'll have to use some trick to find the height difference, and then normally you're going to be asked to find either the velocity or the potential energy. So if you have any other questions, make sure you reply as a comment on Teams.